Welcome to another explainer, where we transform everyday mysteries into scientific mastery. I'm honestly so thrilled you're here today because we're diving right into Form 3 Science Chapter 5, Thermochemistry. You know, this is one of those fantastic topics that takes something you experience every single day, heat, and completely unmasks the hidden chemical machinery operating right in front of your eyes.
Let's actually kick things off with a little mystery. Have you ever wondered how a medical cold pack can just instantly turn freezing cold without ever seeing the inside of a freezer? You literally just snap it, give it a quick shake, and boom, it's icy. And on the flip side, how exactly does a hot pack generate immediate, soothing heat out of thin air? I mean, it feels like magic, right? But I promise you it's 100% pure science.
Here's our agenda for today's investigation. First, what is thermochemistry? Second, exothermic versus endothermic. Third, reactions in the wild. Fourth, in the lab, experiment 5.1. Fifth, real-life hide heat hacks. And finally, number 6, a chapter summary. All right, let's jump in. Section 1. What is thermochemistry? The study of heat changes. So, the crucial thing to grasp here is that thermochemistry is, well, exactly what it sounds like. It's the study of heat or energy changes that happen when chemical reactions take place. Simply put, whenever a chemical bond is broken, heat is absorbed. But whenever a new bond is formed, heat is released. And this entire field relies super heavily on the concept of thermal equilibrium. You might actually remember that from Form 2. Thermal equilibrium is just that state where two objects in physical contact eventually reach the exact same temperature, and they just stop exchanging heat. This concept is absolutely vital because it explains how a chemical reaction transfers heat to its surroundings, like the water in a beaker or even the palm of your hand, until the whole setup just completely balances out.
Moving on to Section 2, exothermic versus endothermic, the twin pillars of heat exchange.
Now, if you ever find yourself getting these two mixed up on a test, there's actually a really easy cheat code. Just look at their Greek origins. Think of exo as exit, meaning outside, right? That's where heat leaves. And think of endo as enter, meaning inside, where heat goes in. And of course, thermic just means heat. So exothermic, heat exits. Endothermic, heat enters. It really is that simple.
Seeing these two heavyweights side by side really highlights their key differences. So, in an exothermic reaction, the chemicals release heat, and that causes the surrounding temperature to rise. And because they're giving away all that energy, the total energy of the final product is actually less than what it started with. Endothermic reactions, on the other hand, pull heat in, which makes the surrounding temperature drop. Since they're actively absorbing heat, the total energy of the product ends up being more than the original reactant.
Next up, Section 3, Reactions in the Wild, Spotting Invisible Chemistry.
Look at this. It's a brilliant illustration of exothermic power in the wild. When you see massive festival fireworks light up the night sky, or a blazing campfire, or actually even just human respiration, that is exothermic energy at work. It's actively releasing heat and light out into the surroundings. Oh, and another incredible textbook example is dropping sodium into water. It triggers this crazy, vigorous, steaming exothermic reaction that rapidly heats up the whole container. The heat is loudly and proudly exiting. But on the flip side, endothermic reactions are quietly absorbing heat all around us. They're a bit stealthier, you know? A perfect natural example is photosynthesis in green plants. They're absorbing light energy from the sun to make their food. Heat is entering. Or think about baking a cake in the oven. That batter sits there, actively absorbing the surrounding heat to transform into a fluffy sponge. And in a chemistry setting, simply dissolving ammonium salts in water will literally pull heat right out of the liquid, leaving you with this surprisingly cold cup of water.
All right, Section 4, in the lab, experiment 5.1, proving the theory.
This is a beautifully simple 4-step process to prove what we've been talking about. Step 1, you just pour 50 milliliters of water into a polystyrene cup, which, by the way, acts as a really great insulator. Now, step 2 is absolutely crucial. You have to leave it for 2 minutes. This ensures the water reaches thermal equilibrium with the room before you record your initial temperature. Then, for step 3, you add your chemical, like sodium hydroxide or ammonium chloride. Give it a stir, and for step 4, just watch that thermometer. If you hit a maximum temperature peak, heat exited, so it's exothermic. If you see a minimum temperature drop, heat entered, making it endothermic.
Now, if you want to score top marks on this experiment in your exams, you absolutely must memorize these variables. We manipulate the type of chemical substance. Basically, we're testing different powders to see what happens. That manipulation causes the responding variable, which is our final temperature reading, to either spike up or drop down. And of course, to keep the whole test completely fair, we have to ensure the constant variable, which is our specific volume of water, remains perfectly unchanged throughout all the trials.
Section 5. Real-life heat hacks. Thermochemistry in medicine.
Okay, this totally solves our opening mystery. Medical instant packs are basically just portable little chemistry sets. Instant hot packs contain chemicals that, when mixed by squeezing the bag, trigger an exothermic reaction. This releases heat straight to your skin, which is just fantastic for relieving muscle cramps because it actually increases blood circulation. On the other side of things, instant cold packs contain chemicals that trigger an endothermic reaction when you break the inner pouch. It rapidly absorbs heat right from your surroundings, or your skin, instantly cooling a swollen injury. It's literally thermochemistry rushing to the rescue.
And finally, Section 6, Chapter Summary. Master your exams.
I'd highly recommend taking a quick screenshot of this slide, as it perfectly summarizes the whole shebang. Remember, thermochemistry tracks heat changes. Exothermic equals heat exits, so the temperature rises. Endothermic equals heat enters, so the temperature drops. Be sure to burn these examples into your memory. Respiration, burning, and sodium plus water for exothermic, and for endothermic, photosynthesis, baking a cake, and dissolving ammonium salt. Plus, obviously, how we apply all this brilliance to medical instant hot and cold packs.
Before we wrap up this explainer, I want to leave you with one final, kind of provocative thought. We know from the fundamental laws of science that energy is perfectly conserved, right? It can never be created or destroyed, only transferred. So, if that's true, where exactly does the heat go when your instant hot pack finally loses its warmth and goes cold? Think about how thermal equilibrium stretches out from your hand, out into the room, and even beyond. Keep asking those big questions, keep exploring the invisible forces all around you, and I'll see you in the next explainer.